So today we're going to look at some pH calculations going between pH and concentration. So this is chapter 8 problems. The first one asking us to calculate the pH of 1.5 times 10 to the negative fifth molar, so that's a molarity, it's got the units of a capital M, solution of HBr. Well, with what I've learned about acids and bases in this chapter, HBr I'm going to assume is an acid. Okay, because it has a proton in it, and acids by definition are protons donors. Okay, so it's going to donate that proton to a base. So let's look at how to do this calculation. So when we're calculating pH, we are given an equation to calculate where pH is equal to negative log of the concentration. So we've seen it where the concentration is represented with brackets and an H plus. Another way of writing this equation is negative log, brackets again, brackets standing for the concentration, and instead of just H plus, H3O plus. Okay, so both of these are the same thing. It's representing that hydrogen. We're seeing what is the concentration of protons, H plus ions, in this solution? That's what it's asking for. So the concentration of H plus ions is this 1.5 times 10 to the negative fifth. So we're going to plug that in to this spot and solve. Since it's an acid, I'm going to assume that the pH is less than 7. We'll look at the pH scale here in a moment. So pH, negative log, don't forget that negative. And then in the brackets, I'm going to put the concentration in molarity. And that is 1.5 times 10 to the negative fifth. So when I enter that in my calculator, I'm going to press the negative sign on my calculator first. Not the subtraction sign, but there's a little negative sign that you should have on your calculator. You then find the log button, parentheses should appear, and that's when you can enter the 1.5, and since it's times 10 to the, depending on your calculator, you might need to do that second EE button, and then negative fifth. Close the parentheses, and it gives me a pH of, we're looking at 2 sig figs, so 4.8. pH doesn't have a unit, okay, it's just called pH. All right, so let's look, I know it's not asking, but it's always good to practice. So let's look at whether this is acidic or basic. So based off of the chemical formula HBr, I would assume it's acidic because it has a proton in it that it can donate. So whenever the proton, and when I talk about a proton, I'm talking about hydrogen. Hydrogen plus. I'm not talking about a proton in the nucleus of an atom. Okay, so HBr is H plus Br minus. Okay, so this H plus here, that's called a proton because it has a positive charge just like a proton does in the nucleus of an atom. But this is a different proton than the one in the nucleus because it's hydrogen with a positive charge. Okay, so those words are have different definitions. Okay, so based off of the chemical formula, I would assume it's an acid. Well, we've calculated the pH, and the pH will tell us. So pH goes from 1 up to 10, or 14, sorry, 11, 12. Okay, so what I have written here is my pH scale. And if you've watched the PowerPoints, I've explained this in more detail there. So my pH scale goes from 1 to 14. So 7 is neutral. You get what I mean? I know I spelled neutral wrong. But to the right, so higher than 7, this is basic conditions. Lower than 7, I see I missed a 6 there, is acidic. So the pH of this compound, HBr, falls right in between. So it is acidic. So let's look at the next question. So pH helps determine if a compound is acidic or basic. So before we solve this one, we're given the pH in number 2. pH is 3, so is that acidic or basic? According to our pH scale. It's acidic. It's less than 7. Okay, it's actually more acidic than this HBr. And that is true. HCl, hydrochloric acid, is more acidic than HBr. That's nothing that you would have to know. You would base that off of the pH you are given. Okay, so this one's having us calculate the proton concentration of a solution of HCl. So in brackets here, that's saying that it wants the concentration, and they could have written either this H3O plus or just H plus. Both of these mean the same thing. You calculate them the same way. And how we calculate them is by taking 10 to the negative pH. Oops. So this is our equation that we're using to calculate concentration. We're 10 raised to the power of negative pH. Okay, so when you enter this into your calculator, and that's the trickiest part of these problems really, is just figuring out how to put it in your calculator. So we have 10, and then to the negative, the pH given was 3, so it's going to be times 10 to the negative third. Okay, and on your calculator, we basically rearranged this negative log calculation to come up with this one, right? You don't have to know how to rearrange it because you're given both equations. But to calculate it, you want to press the second button and then your log button. And what that should do is on your calculator, when you press second log, it should show on your calculator 10 and then this little to the power of sign. Then it will give you parentheses, and in that parentheses is where you're going to enter this negative 3 that you have here. Don't forget the negative. Okay, so when I enter my negative 3, it tells me that my concentration of H plus ions is 0.001. Or, if you have it in scientific notation, 1 times 10 to the negative third. So both of these are correct. And of course, don't forget your units. So when we're measuring concentration with these calculations, it's molarity, so you just need a capital M after the answer. All right, let's look at this last one now. So let's start by just seeing if it's acidic or basic. Because they gave us the pH. pH of this lake water, the sample of lake water, is 6.40. So looking at our pH scale, 7 is neutral. And this is just a little bit lower than 7, right? So it's slightly acidic, but not too much. Okay, very close to neutral. So we're going to calculate the concentration of H plus ions in this sample of lake water. So it's the same calculation as we did in number 2. So I'm going to start by giving my equation ready before I plug in. Okay, so 10 raised to the negative pH. So it's going to be 10 to the negative 6.40. And when I enter this in my calculator, I'm going to press second log, because my second log function on my calculator has a little 10 to the x above the log function, and that's what I'm looking for, because 10 raised to the x is 10 raised to a power. Okay? So when I press that second log, it gives me the number 10 with a little raised to the power sign in parentheses. In the parentheses is where I'm entering that 6.4. And everybody's calculator might be slightly different. If you're having any trouble figuring this out, don't be afraid to send me an email. We can meet up via FaceTime or any virtual platform that you're comfortable with to figure it out. All right, so when I enter that in my calculator, I get 3.98 times 10 to the negative, what is that, negative 7? Yes, and that's concentration, so it's molarity. Depending on your calculator, it also might have just given you in normal notation where it should have 6 zeros and then a 398. So both of these are correct. And I want to point out with the concentrations that notice the concentration in number 3, it's times 10 to the negative 7th, so very, very small number, right? Number 2, it's 10 to the negative 3rd, so not quite as small. So the higher the concentrations, the more acidic it is, because this concentration of H+, that's how many H+ ions from the acid are present. So if there's a lot of H+ ions present, that means it's a very acidic solution. Okay, so the concentration can also tell you how acidic it should be as well. So number 2 is the most acidic concentration-wise, then number 1, and then number 3. All right, let's look at oxidation and reduction reactions. So here we have 2 balanced reactions, and they are single replacement reactions, which are oftentimes redox reactions. So with redox reaction, it's an oxidation reduction. They always happen in pairs. So one element is oxidized and another element is reduced at the same time, because one is losing electrons and the other is gaining the 2 electrons that the other one lost. Okay, so the PowerPoint shows different mnemonic devices to remember which one's oxidized and which one's reduced. I just have a few of them over to the right here. So Leo the lion says Gur is one of them, and that stands for lose electrons oxidized, and then gain electrons reduced. One that a lot of people like as well is just this number line here. And what this number line is showing that if your charge is changing, so going up, it is oxidation. Because if you're losing electrons, right, you're losing negative charges and going into the positive area. For reduction, that's going the opposite direction because you're gaining electrons. So if you gain electrons, you are going into the negatives because electrons are negatively charged. Reduction going down also is a good way to remember that. So let's look and see what's happening. Let's tackle this first one. So the first step to figuring out who's oxidized and who's reduced is figuring out the charges of all of the elements given in this chemical reaction. So whenever you have an element in its pure form, its charge is 0, it's neutral. So hydrogen, diatomic hydrogen, that's how it exists in nature. It's in its pure form, its charge is 0. Fluorine, same thing. It's one of those 7 that forms a diatomic in nature, so it is 0 as well because it's just fluorine atoms by themselves. Okay. Now, on the product side, we have a compound. And with this compound, we need to look for the charges. So hydrogen is in that first column. It's with the alkali metals, and it forms a +1 when it's in a compound. Fluorine then, it's a halogen, forms a -1 when it's in a compound. So, now I'm going to write some half reactions showing how each element is changing from the reactant side to the product side. I'm going to start with hydrogen. So I have hydrogen, neutral, on the reactant side. It forms 2H+. Okay, so why am I saying 2? Because of this coefficient right here. That's saying I have 2 hydrogens and I have 2 fluorines. Okay, which makes sense. In order for this to be balanced, I need 2 here because there are 2 hydrogens on the reactant side as well. All right, so I'm going from a 0 to a +1. So let's check that out. If I'm at 0 and I go upward direction to +1, I'm going up on the number scale. If I'm going up, that means it's oxidation, which is correct. So hydrogen is the one that is oxidized. Another way to look at it, if the number scale isn't clicking with you, is to look at what's happening here. Okay, so to go from a 0 to a +1, that means that hydrogen had to lose electrons, because when you lose an electron, you're losing a negative and becoming positive. Okay, so losing electrons is oxidation. So the electrons I'm going to put on this side. How many electrons? 2. So the reason I put them on the product side is because in order for hydrogen to be neutral, these two H pluses need to gain 2 electrons. Okay? So when you're writing these half reactions, if your electrons are on the product side, the right side, it's oxidation. And luckily, it's a multiple choice test, so you won't have to write the half reactions. You just need to figure out who's oxidized and who's reduced. Okay? So if that electron thing's not clicking with you, don't worry about it, as long as you can figure out if hydrogen was oxidized or reduced. All right, well, now we're going to look at fluorine. Obviously, since they happen in pairs, fluorine's going to be reduced. But let's do the work to make sure. So fluorine is neutral on the reactant side, and it goes to be 2 fluorine anions on the product side. All right, so it goes from a 0 to a -1. So on my number line, I'm going down the number line. If I'm going down, I'm being reduced. So it is in fact reduced. How many electrons are needed? Well, I have 2 fluorines. Each fluorine's a -1, so that means I need 2 electrons in order to reduce both of those fluorines. So the electrons go on the reactant side. This is because if I add those 2 negative charges to that 0, I will get 2 negative fluorines. So what do you need to know how to do? You need to know how to identify who's oxidized and who's reduced. You need to be able to identify how many electrons are involved. Okay, and for that, you're going to be using subscripts, you're going to be using coefficients in combination with the charges. Last but not least, you need to be able to name who's the oxidizing agent and who's the reducing agent. And the nice thing about this is it's the opposite. So what I mean by that is the element, in this case hydrogen, that is oxidized, that is the reducing agent, because it is the element that is reducing fluorine. It's doing the work. For fluorine, it is reduced, so that means it must be the oxidizing agent, because it is oxidizing hydrogen. This is why they're happening in pairs. So the 2 electrons that hydrogen is losing, because it's oxidized, so it's losing electrons, so those 2 electrons that it's losing, it's giving to fluorine so that fluorine can become a -1 anion. Okay, so that's why they happen in pairs. You need those electrons to come from somewhere. Let's try another one. So down here we're looking at copper 2 oxide reacting with hydrogen gas to make copper and water. Okay, so this is balanced. What we need to do now is figure out the charges. So transition metal, those are the fun ones. We don't know the charge on the transition metal. They have multiple variable charges. So we look at the charge on its partner. When I look up oxygen on the periodic table, it's a -2. There's only one of them. So if I have a -2 on the oxygen, what do I have to have on the copper to make this compound neutral? I need a +2. +2 plus a -2 equals 0. Okay, so that compound as a whole is neutral with a +2 on copper, a -2 on oxygen. Now looking at H2, much like up here, it's an element in its pure form, so it is neutral, zero charge. On the product side, we have copper by himself now. So copper by itself is an element in its natural state, so it is also neutral. Okay, well let's look at H2O. The charge on hydrogen is a +1, oxygen is a -2. So now that we have the charges, let's split these guys up and see who is oxidized and who is reduced. So we have copper on the reactant side going from a +2 to neutral on the product side. Okay, we have oxygen going from a -2 to a -2. All right, well, let's lastly do hydrogen here. Hydrogen's going from a neutral to +1. Well, first thing I'm going to notice is oxygen here. Did anything change with oxygen? Went from a -2 to a -2. So did it gain or lose electrons? No. So that was neither oxidized or reduced. So now I'm down to copper and hydrogen. So copper went from a +2 on the number scale, downward direction to 0. So if you're going down the number line, it is reduced. It is reduced because it is gaining electrons. Gain electrons reduced. Because in order to go from a +2 to a 0, it needs to gain negatively charged electrons. How many electrons? To go from a +2 to a 0, you need a -2. So if you need a -2, that means you're adding 2 negatively charged electrons to get there. Right? So by default, I know that this one down here is going to be oxidized. But just to make sure, it's going from a 0 to a +1. So upward direction, yes, it is oxidized. It loses electrons to go from a 0 to a +1 charge because electrons are negatively charged. So we have 2 electrons on this side because there's 2 hydrogens, so I need 2 electrons, 1 for each of them, to get back to 0. All right, last but not least, who's the reducing agent and the oxidizing agent? It's just the reverse. So whoever's reduced, that is the oxidizing agent. Whoever is oxidized, that is the reducing agent. I'm spelling this horribly. All right, I do want to try one more. Let's give you a little bit more practice here. I know we did do this in Lab 9 as well, so you've already seen this before, and you might have watched the PowerPoints, but practice makes perfect, so let's give another shot here. So this one I wanted to do because I wanted to show you one with a little bit more coefficients, because this one's a little bit harder to figure out how many electrons are involved. And that is something you need to be able to figure out given the equation. It's a big one. All right, so we have manganese oxide reacting with aluminum to get manganese by itself and aluminum oxide. All right, well, charges, that's our first order of business. Manganese oxide, well, I just named it wrong. Why? Manganese is a transition metal, so I need a Roman numeral after the name of the metal to indicate its charge. Since it's a transition metal, I can't figure out its charge just by looking at it. Okay, I need to look at its partner. So oxygen, its partner, is a -2. I'm going to write this one out a little bit longer. So how many oxygens do we have? 2 of them. So I have 2 oxygens, each with a -2 charge. So what's my total charge on oxygen? It's going to be a -4. So how many manganese do I have? Looks like just the 1. So what's the total charge I need on the cation side to balance out this -4? I need a +4. Okay? So that entire charge is going to go on that 1 manganese. That way the compound as a whole is neutral. All right, so now that we have the charges figured out of that ionic compound, let's look at aluminum. Now aluminum, when it's with a partner, is a +3. But aluminum is not with a partner on the reactant side. It's an element by itself. All elements by themselves have a neutral charge. It only gets the ionic charge when it combines with a partner and they switch electrons or transfer electrons from one to the other. All right, so manganese is by itself on the product side. Element by itself, 0. Aluminum, we just said, +3. Oxygen, same as over here. It's combined with somebody else, so it's going to have a -2 charge. It's in an ionic compound. All right. Now I have my charges. So I have 3 possible choices to choose from. So let's see who's doing what. Okay? So let's start with manganese. And when I write these half formulas, make sure you're including those coefficients because that's going to help you figure out how many electrons are involved. So I have 3 manganese, each of them have a +4 charge. Well, on the product side, I still have 3 manganese, which I should if it's balanced, but now each one has a 0, neutral. All right, so something definitely happened there. We went from a +4 to a 0. Okay, let's look at oxygen. I have 3 O2s with a -2 charge. On the product side, I have 2 O3s, keeping it balanced, right? 6 and 6 oxygen atoms on both sides with a -2. Last but not least, 4 aluminums. And I have 2 Al2s, which is still 4 aluminums, but on the product side, the charge is a +3. Notice I forgot the charge over here. It was neutral. So let's see who's doing what. Manganese, something's definitely happening, so I'm keeping him. Oxygen went from a -2 to a -2. So any electrons changing there? No. If the charges are the same on both sides of the equation, it is not part of the redox situation. It wasn't oxidized, it wasn't reduced. Okay, so I'm going to erase this one because we are not going to characterize him. All right, and the last guy, going from 0 to a +3. So the charge definitely changed. Okay, so if the charge changed, something happened. It was either oxidized or reduced. So back up to magnesium. Let's figure out what's going on with this guy. We went from a +4 to a 0. So we're way up here at the +4, and we're going which direction? Downward. We're reducing all the way to 0. Okay, so if we're going downward, that is reduction. So this was the one, manganese was reduced. It was reduced because it's gaining electrons. It needs to gain electrons to go from a +4 to a 0. Now, aluminum went from a 0 to a +3. So aluminum started at 0 and went the opposite direction, up to a +3. So aluminum was oxidized because aluminum lost electrons. So let's figure out how many electrons, because this is going to be a lot. Okay, so we have 3 magnesium atoms. Manganese, sorry, not magnesium. So I'm going to write them down here with their charges, just so you can kind of see how this is all worked out. So I got 3 +4s. Okay, I need to get so that I have 3 zeros, essentially, right? Well, how do I get from a +4 to a 0? How many electrons do I need? I need 4 electrons. It's asking, okay, to go from a +4 to a 0, how many negatives do I need? I need -4, right? So I need 4 electrons for each one. But I have 3. So I need 4 electrons to go from +4 to 0 here, 4 electrons to go from +4 to 0 here, and then 4 electrons there as well. Okay, so I need a -4 here, a -4 here, and a -4 here, all to get to these zeros. So how many total electrons is that? Because this -4, that's representing the electrons. So I need 4, 8, 12. So 12 electrons are needed to go take those 3 manganese atoms with a +4 and make all of them neutral. Okay, and you can see the same thing here. It's just a little bit different because here we have 4 instead of 3. So let's do my aluminum atoms. So I have 4 aluminums at 0. But the aluminums are going from 0 to 3. Okay, well, how many electrons do I need here? It should be the same, because if the manganese are losing 12, manganese are gaining 12, they're getting them from the aluminum. So aluminum has to have 12 to give. All right, so if I want to go from a +3 to a 0, how many electrons do I need? 3. I'm going to put -3 electrons because electrons are negatively charged. For this aluminum atom, I need -3 electrons as well. -3 electrons and -3 electrons. So how many total electrons? 3, 6, 9, 12. So I need 12 electrons here as well. So aluminum, since it's oxidized, is losing these 12 electrons and giving them to manganese so that manganese can become neutral on the product side. So to finish this guy off, let's label the oxidizing agent and the reducing agent. I also have a video with Tyler DeWitt. I've done several of his videos and had positive feedback explaining oxidation reduction if you want a different take on it. So hope this helped.